Hi, welcome to the Olympiad geometry. Let's continue our study. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. So let's continue on the geometry treasure, Incenter, Excenter, Encircle, Excircle properties. Property 7, if you just look at these three properties, they basically have the similar problem set, and let's prove it. Property 7, Excircle circle OB of triangle ABC is tangent to BC, BA on EF respectively. Excircle circle OC of triangle ABC is tangent to CB, CA on DG respectively. DG meets EF on P. Prove that PA is perpendicular to BC. So I think in the past video, maybe in the very beginning of this channel, the Menelius theorem, we proved this problem before. The reason I want to still write it here, just because this is a large set of problems. Let's start with this one as a simplest one, which is still a national computation problem. Okay. So we have our triangle first, right? This is our triangle ABC. And we want to find the circle. We want to find the circle OB, which is X circle relative to the vertex B, right? So we want to find the angle bisector here, and we want to find the angle bisector here. So this point would be OB. And we want to find angle bisector here. So this point is OC. Now we have our triangle and excenters. We know that OB is tangent to BC and BA on point E and point F. And OC is tangent to BC on point D. Tangent circle OC is tangent to AC on point G. Now we want to connect DG and we want to connect EF. So DG and EF meets on point P, and we want to prove that PA is perpendicular to BC. Okay, so for these problems, or these sets of problems, one idea is that we find the lines that are perpendicular to BC first, that are passing through A and perpendicular to BC. We find this line first. So let's assume this line L, right? AH is perpendicular to BC, and call AH as L. So let's say this line L meets DG on P prime, and line L meets EF on P double prime. We just need to prove that P prime is the same point as P double prime. And the idea is that if we can find AP prime to HP prime equals to AP double prime to HP double prime, then we prove that P prime is P double prime and is P point P, right? Okay, so look at here. How can we get AP to HP? The very simple idea is to use Mendeley's theorem on the triangle AHC and the line DGP prime. So we have AP prime to HP prime times HD to CD times CG to AG equals to 1, right? You may ask why I want to choose the triangle AHC and DG line DGP, right? If you look at here, we know that CD is a tangent line of the circle OC, CG is a tangent line of circle OC. That means we have CD and CG, they're equal. And if you look at here, we can, if we choose the triangle AHC and the line DGP as a intersection line, then we can have CG and CD cancelled, right? That can help us to get some result. Based on this, we get that AP prime to HP prime equals to AG to HD. Okay, so we have AP prime to HP prime equals to AG to HD. And similarly, we can do the triangle ABH and line EFP with Mendeley's theorem. Then we have AP double prime to HP double prime times HE to BE times times BF to AF equals to 1, right? So from this one, we got AP double prime to HP double prime equals to AF to HE, right? Now we have AG to HD and AF to HE. So AP prime to HP prime equals to AP double prime to HP double prime is equivalent to prove that AG to HD equals to AF to HE, right? And this one is equivalent to AG to AF equals to HD to HE, right? And we know that HD to HE, because the OCD and AH and OBE, the parallel lines. So HD to HE equals to HD to HE equals to OCA to AOB, right? That's HD to HE. And if you look at the triangle OCGA and the triangle AFOB, because they are all right triangles, and because OCOB is an angle bisector of angle BAG and angle CAF, and we know that angle BAG equals to angle CAF, that means the angle OCG equals to the angle OCAG equals to angle OBAF, right? Meaning that triangle OCAG is similar to triangle OBAF, which means OCA to AOB equals to AG to AF. So you can see we want to prove this one, we just did that, which means AP prime to HP prime equals to AP double prime to HP double prime, which means P prime and P double prime are the same point. Okay, that's for the first property. And the second property is a similar problem set here, just a different, I'll just draw it here. Again, we have our triangle A, B, C, and we want to find the Excenter. This one is OB, and this one is OC. Right, so OB is perpendicular BC to point E, and OB is perpendicular to AC. This point as F. Right, look at the difference. In previous one, we have OB perpendicular to AB on F, right? Now we have OB perpendicular to AC on F, right? The circle OB is tangent to AC on F. That means OB F is perpendicular to AC. Okay, and we have OC, circle OC tangent to BC on point D, and circle OC tangent to AB on point G. Now we want to prove that DG meets FE on point P, and we want to prove that AP is perpendicular to BC. Okay, so the idea is the same. Let's just draw the perpendicular line AH first, right? Let AH meet DG on P prime, and let AH meet EF on P double prime, right? And now think about how can we choose a triangle. And of course, we are still going to use the Mendel's theorem. So we need to choose a proper triangle, and we need to choose an intersection line. In previous one, remember that we have CD equals 2, that's CF, right? Now we have BD equals to BG, which means we want to choose these two as a segment shown in the Mendel's theorem, which means that D and G should be on the intersection line, which means DGP will be the intersection line, and then we have to choose the triangle ABH, right? Then it's easy to write it down as AP prime to HP prime times HD to BD times BG to GA equals to 1. Similarly, for triangle AHC and the intersection line EFP double prime, we have AP double prime to HP double prime times HE to CE times CF to FA equals to 1. And notice that BD equals to BG, CE equals to CF, which means AP prime to HP prime equals to AG to HD, and AP double prime to HP double prime equals to AF to HE, right? And we already proved that triangle AOCG, well, we didn't, right? But it's the same, because the triangle OCAG and the triangle OBAF, they are all right triangles, and because the OCOB is the angle bisector of angle BA, for example, X, Y, right? The OCOB is the angle bisector of angle BA, the angle BAX and angle CAY, right? And angle BAX equals to angle CAY. That means angle OCAG equals to angle OBAF equals to half of the angle BAX, which means triangle OCAG is similar to triangle OBAF, right? That means AF to AG equals to, see here, basically we just need to prove AP prime to HP prime. We want to prove that AP prime to HP prime equals to AP double prime to HP double prime, right? We want to prove this one equal, these two are equal, then we just need to prove that AG to HD equals to AE to HE, sorry, AF to HE, right? Which means we need to prove that AG to AF equals to HD to HE. And we already know that AG to AF equals to OCA to AOB, and OCA to AOB equals to DH to HE. Then we prove this one. Okay. So for the third problem, it's a little more difficult. Let me explain the problem set. Problem is saying that similar to this figure, but we have the connection of that if we extend the CG, right? If we extend the CG, meets the circle OC on a point, and let's call it S, right? And if we extend DF, right? Extend DF, meet circle OB on a point, let's call it T. Then we want to prove that the intersection point of SD to CT let me see. Did I make something? No, not CT, TE, right? TE. So SD meet TE on point U, then we want to prove that AU is perpendicular to DE. Okay, let me draw this one. So we have triangle ABC here. And we have the angle bisector. This one is OC, this one is OB, right? And OB is perpendicular to I think this is D, this is E. And this is F. This tangent point is G. Now the question is that when we connect CG and BF, right? So CG right, CG meets the circle OC on a point, let's call it S, and the BF meets the circle OB on another point, call it T. Then we want to prove that the intersection point of SD and TE, these two lines meets on a point U. We want to prove that AU is perpendicular to BC. Well, the figure is not well plotted, but you know what I mean here. So we want to prove that AU is perpendicular to BC. So this one would be kind of difficult to prove if we just use the Mendel's theorem, because the point S and T are not very simple to associate with segments, right? So here we need to use a harmonic bundle. That's the easiest way to solve this one. I think I made the harmonic bundle properties video in the series of the geometry treasure, which just include the most important ones and the core idea of the harmonic bundle. I think I will make harmonic bundle video in future, at least small properties based on the geometry cherry book. Okay, so for here we can just take a look at this one, because CD here, let's see, the OC, the circle OC is tangent to AC on a point, let's call it L, and the circle OB is tangent to AB on a point, right? Let's call it K. Then we know that SDGL, right? SDGL. This SDGL, because CD and CL are the tangent lines of the circle OC, so we know that SDGL is a harmonic quadrilateral. Right. That's for the SDGL. Similar for TKFE. TKFE is also a harmonic quadrilateral because BK and BE are tangent lines, and BFT intersect the circle OB, right? So based on this, then we know that, let's think about a line. So we can extend the DG, we can extend the DL, right? And we have DB here and SD here. That form a harmonic bundle, which means if we have the connection, because we have the DL perpendicular to AH, right? Let's call it H. DL meets AH on point P1, and the DG meets AH on point P2, right? In the first two properties, we just prove that AP1 is perpendicular to BC, and AP2 is perpendicular to BC as well, right? So we know that P1, A, P2, they are all this line is perpendicular to DC, right? So DB meets, we have the DL, we have the DG, we have DB. DB meets A, P1A, P2 on the point H, right? And then DS meets this one on another point. Then we know that this forms a harmonic bundle, which means P1, P2, H, and let's call it U1. Right? P1, P2, H, U1. It's a harmonic array. And similar for this side, let's call it U2, would be another harmonic array. But they are on the same order as P1, P2, H. These 3 points are fixed, which means U1 and U2 must be on this line, right? Which means U1 and, the distance from H to U1 equals to the distance from H to U2, because they all form the harmonic array. Then we know that U1 and U2 are the same point, and also U1 and U2 on the perpendicular line P1A, P2H. So that's the easiest way I can think of to prove this one. And also this is a method that I introduced in the book. So other than that, I think just to use the main list theorem would be difficult and very challenging for this problem. Okay, that's our introduction on these kinds of problem, but we will have more about this. You will see lots of problems associated with this kind of perpendicular relation that we want to prove. Okay, I hope you like this video. See you in next one. Thank you.